Okay, so start with the review. Of quantum mechanics. So in quantum mechanics, the state of a system, suppose we have a system, its physical state is described by a vector, okay? By a complex vector. And I should say is usually described, because we shall see there are more general circumstances where a complex vector does not suffice to describe the state of the system. Okay, and that general case is going to be called case of density matrix. Now, a lot of undergraduate quantum mechanics course does not teach density matrix, which is unfortunate, but thankfully for our purposes, we will need density matrices. In fact, you will see that you have already seen what a density matrix is. So what do I mean by a complex vector? So this is not going to be a mathematically rigorous introduction, but more of a, example-based introduction. So for example, let's take one example. Suppose we have a spin half particle and we want to describe its spin degree of freedom. So it's spin degree of freedom of a spin half particle. So it's a fact of nature that quantum particles come with quantized angular momentum, which are quantized in units of h bar by 2. So example of a spin half particle is an electron. And so the vector describing the spin half particle will be a 2-component vector. And you might ask, why is it 2-component? Well, to learn that, you have to actually take a quantum mechanics course where there will be a mathematical derivation of this fact. Okay? So this is a vector. It's a 2-component vector where psi1 and psi2 are complex numbers. Right? So I can say that psi is an element of the vector space C2. Okay? So that is, say, one example of a state vector. Another example, so there are other degrees of freedom. And these are such as the position of a particle, the momentum of a particle, or the energy of a particle, or even the orbital angular momentum of a particle, which is different from spin, although they share a lot of similar properties, but they're intrinsically different. In fact, the spin, the degree of freedom that we call spin, has no classical analog, whereas all these things have some classical analog. So these degrees of freedom are described by a complex wave function. Okay, so they're described by a function which is complex, and it's a function of space-time. And a lot of time I will just denote this as like that. Okay, rather than at least when the context is clear. Now, you might say, why do we have these different rules for spin and for other degrees of freedom? There's actually a unitary, that is a unified point of view, in which you think of psi of x as an infinite dimensional vector. Okay? For example, this vector, this two-component vector, we can denote the component like that, right? Where I goes from 1 to 2. Similarly, you can think of this as a vector psi whose component is given by the index x. So how many indices do we have here? We have a continuum of indices, right? So therefore, this is an infinite dimensional vector, right? So it's some kind of, element of a C infinity space. Okay. So this is just a different way of looking at what we call a function. Okay. So an example of a wave function, so these are called wave functions. So an example of a wave function, say at a given time, is going to be, say, some normalization constant e to the power minus x minus vt whole squared by a, well, let's say a squared. So what will this wave function look like? So it's just an x dependent, so let's just call this x. So this wave function will look like this, that if you have the x-axis over here, and this is a real wave function, then it's a Gaussian whose spread is going to be, I think it's what, a over 2 or a, or 2a? Okay, of the order of a, and whose center is given by vt. So it's a wave function which is traveling to the right. Okay. So this is not really a realistic wave function, because what happens is that in a realistic quantum system, as the wave function moves, it actually spreads out. So there will be some time dependence here, some time dependence here. But I'm just giving you like a rough idea of what a wave function can be. Okay, so this is how the state, all the information about a quantum state is encapsulated in a wave function or a wave vector. So we are going to denote a generic vector or a wave function by this sort of symbol. This is called a ket. And this is a notation that was discovered by Dirac, not discovered, invented, and he called this is a conjugate. If psi is a vector, you can take Hermitian conjugate, and this is called a bra, and this is a number, so that you have a bracket. So that's the root of this nomenclature.